This is lesson 13 of the Quantum Mechanics, a mini lecture series titled Balmer's Formula. So in the previous lesson, I talked about the formula put forth by the Swiss maths teacher, Johann Balmer. It's written as follows: F equals R 1 over n sub f squared minus 1 over n sub I squared. Okay, where F is the frequency of light, R is just a number. It's called the Rydberg constant in honor of Rydberg, a guy who worked on Balmer's formula, who refined it further later on down the track. And that's equal to, it's around 3.29 times 10 to the 15 cycles per second. N sub f and n sub I, these are just numbers. These are whole numbers. And so what Balmer found was that in order for his formula to work, to match the corresponding frequencies observed in the lab, let's say for hydrogen, okay, there are 4 distinctive spectral lines in the visible part of the spectrum. N sub f has to equal 2, and n sub I can only be 3, 4, 5, 6. Okay. And n sub f corresponds to the final energy state. N sub I corresponds to the initial energy state. So something was hinting that perhaps this has got something to do with the underlying building blocks of the gases that were being observed, the elements. They were made up of something, okay, but no one was really able to figure out what was going on. Okay, energy states that corresponds to something happening at the very tiniest of levels, the atomic level. I'll just show you the power of mathematics. So experimental values versus Balmer's formula. Just a comparison. Okay, Balmer's formula worked. It was very accurate. And I'll have frequency here. So the measured frequencies in the lab, let's say, one of the spectral lines, 457.170 megahertz and 617.190 megahertz. Now, these were what was measured in the lab. So I'll put in brackets lab. Now, Balmer's formula for the first one, 457.171 megahertz. Second one, 617.181 megahertz. So very, very close correspondence. Very close correspondence. Now, Balmer also predicted that there was more lines which couldn't be measured, okay, at the time in the UV, ultraviolet, and infrared. Okay, emission lines that you couldn't see with the naked eye, because the naked eye can only pick up colors between 400 to 700 nanometers, okay, wavelength. Anything beyond that, above that or above 700 or below 400 is not visible to the naked eye. Okay, so Balmer also predicted that there should be more spectral lines. And so these different lines, okay, so the visible, ultraviolet, infrared, these different lines suggested an energy diagram, okay, as emission or absorption of light from an object. In terms of an increase or decrease in its energy, okay, an oscillator or something like that. So I'll draw just a quick sketch of an energy diagram. Suppose I've got energy along the y-axis. So let's suppose I've got n equals 2, n sub f, let's say. N equals 3, n equals 4, n equals 5, ... So transitions corresponding to the UV part, okay, where they'd end up in the energy. Actually, what I should do is I should just write it down here. So there were different line series, Lyman, Balmer, Paschen, and brackets. Okay, there were 4 different line series discovered. Lyman was in the ultraviolet, Balmer was in the visible, Paschen in the infrared, and Brackett in the infrared as well. Okay, so Balmer, 1885, Lyman, 1906, between 1906 and 1914, Paschen, 1908, and Brackett, 1922. Now, n sub final for the visible part of the spectrum for Balmer, NF equals to 2, Lyman, NF equals to 1, Paschen, NF equals 3, and Brackett, NF equals 4. Okay, that's your final state that you can have. So draw a proper sketch. Let's just put this for now. Actually, we'll just use n, right? N equals 1. Oops. Draw a better sketch. N equals 2, n equals 3, n equals 4, n equals 5, n equals 6, n equals 7, n equals 8, n equals 9. Okay, for Lyman, I had to end up at n sub f equals to 1. So like this, these are the possible transitions. So I'm just going to quickly do this. So for UV, you'd get these range of energy transitions. For visible, you'd get these transitions. Okay, V for visible. And for infrared, we get these ones. And what you would notice is UV would have larger gaps between the final and initial states. Next up is visible, and then followed by infrared. And this makes sense. Why? Because if you remember, UV is very high energy, I should say, relative to, let's say, visible, which is low energy, visible and infrared. And so longer arrows here, as shown in the UV energy diagram transitions, longer arrows indicates higher frequency of light, and low energy, low frequency, which explains why you can see the visible spectral lines as opposed to the UV. Okay. But yeah, so still nothing was, there was still the mystery of what the underlying physical explanation of this was. Okay, what made up the actual elements? What was going on? Why did this actually work? That question was still outstanding.